2003, researchers got the surprise of a lifetime when they discovered a new human relative in a cave in Indonesia. This cave was called Liang Bua, and this human relative was called Homo floresiensis, and it was surprising for a lot of different reasons. Homo floresiensis bucked a lot of trends because it was a pretty recent hominin, only going extinct around 50,000 years ago, and its brain case was tiny. In fact, its whole body was tiny. Homo floresiensis would have been 3.5 feet tall as an adult, and this condition wasn't pathologic. Every member of its species would have been similarly tiny. It wasn't like they were Homo erectus, but, with dwarfism or whatever. No, it seemed that Homo floresiensis was small due to a common ecological phenomenon called island dwarfism. Island dwarfism occurs when a population of organisms find themselves on an island where there are now fewer resources, and they evolve smaller body sizes to accommodate this change. It's not uncommon, and in fact, one of the other residents of the island of Flores, where Homo floresiensis was found, is Stegodon, a dwarfed elephant. Homo floresiensis was a big deal because, in part, what it showed us is that there are many ways to be a late surviving member of our genus Homo. Not every member of our genus is characterized by these big, bulky brains and complex tools. It was another blow to this human exceptionalist march of progress, this idea that all hominins were sort of trying to become like Homo sapiens with all of our species' idiosyncrasies, because Homo floresiensis seemed to do just fine with its itty-bitty brain and super basic tools. And also, it was little, the littlest hominin that we had ever discovered, and that's really cool and interesting and bizarre, and it's outdated. The new smallest hominin is 3.3 feet tall, and it comes from South Africa, and I want to tell you about it. Hello, my gentle and of course very modern apes. My name is Erica. This is Gutsick, and what we do here is we talk about the latest finds in paleoanthropology, primatology, biology generally, just things that I find interesting in science, and we debunk a lot of pseudoscience. And as I said, today we're talking about a brand new fossil which was published that came out of a place called Swartkrans in South Africa. And as I said, this thing is setting records. The fossil is a really marvelous, fully articulated leg comprised of a partial pelvis, a femur, and a tibia. That's going to be part of the hip, the thigh bone, and the shin bone. While we have a treasure trove of hominin fossils, and hominins are any apes that are more closely related to humans than they are to our closest living relatives, chimpanzees, essentially they comprise the lineage of critters that lead in our direction after our split with chimpanzees approximately 7 million years ago. But we don't typically get articulated remains. We have some, don't get me wrong, but they're rare. Articulated just means that the bones are found still put together as they would have been in life, more or less. And obviously, the big perk of having articulated remains is that you know for a fact that those bones came from the same individual. So I know you're just champing at the bit. You're like, wow, what's this fossil called? Who is it from? Well, the fossil is called STW1/HR2, and it's from a hominin that most people haven't ever heard of, called Paranthropus robustus. Allow me to give you a quick rundown of human evolution. The very first hominins after our split with chimpanzees don't look like much. They look very apish, and that's due to the nature of evolution in general, where when two lineages converge on their last common ancestor, they look more like that common ancestor, and they look more like each other too. The first probable hominins are a little triplet known as Sahelanthropus chilensis, Auroran and Ardipithecus, including species Ardipithecus ramidus and Ardipithecus cadaba. Now, while they look pretty primitive, they look like Miocene apes, they actually have a couple of hints that sort of betray their hominin allegiance. In the case of Sahelanthropus and Auroran, these remains are a lot more fragmentary, and so it's limited to aspects of the basicranium, the canine teeth, and an orthograde or upright posture, as well as aspects of the femur. But in the case of Ardipithecus, we actually have wonderfully preserved remains, including a phenomenal partial skeleton that reveals it's almost certainly a hominin. It has some telltale signs that links it with later hominins and even with humans, including a short ilium that is very familiar when compared side by side with humans, chimpanzees, and australopiths, as well as definitively reduced canine tooth size that are sexually monomorphic, meaning males and females have the same size canine teeth, and an orthograde or upright posture. Basically, this is a run-of-the-mill type of ape that is capable of coming down from the trees and walking upright decently efficiently, certainly more efficiently than anything that came before, when it needs to, which is exactly the type of precursor that you need before you get to Australopithecus. Australopithecus is the genus that comes next, and this genus is extremely well represented with numerous species and hundreds of individuals interspersed amongst those species. Unlike the hominins that came before, these things are very clearly hominins and very clearly more similar to humans than they are any other ape. They were definitively upright and bipedal when they came to the ground, which they evidently did fairly often, given the reconstructions of the environments they lived in weren't these dense rainforests, but rather savannas or mosaic environments, where they were savannas interspersed with clumps of trees. We know these things were bipedal or upright walkers because they have all of the same characteristics that allow humans to be bipedal upright walkers. They have inline big toes for toeing off when they walk with 3 arches in their feet. They have a valgus knee that keeps the weight in a singular column. They have a bowl-shaped pelvis with the iliac blades being in the sagittal plane. Knuckle-walking chimps, in comparison, have their iliac blades or their hip bones in the coronal plane or sort of side to side. These guys use their sagittally oriented ilium the same way that we do, to anchor powerful gluteal muscles and strengthen the pelvic floor. They also have an S-shaped spine, more like humans, with the human number of lumbar vertebrae. In addition, they have an anterior or forwardly placed foramen magnum. That's the hole at the base of the skull whose position and orientation can tell you a whole lot about how a critter moved. In a chimpanzee, as you can see, it's sort of in the back or posterior portion of the skull, and it's also angled backwards. In the case of the human, it's forward and angled forward. And the reason is because the position and orientation of this foramen magnum is related to how the animal holds its head. In humans, the position tells us that this animal, that we hold our head on top of our vertebral column in an orthograde or upright posture, suggesting that we walk upright. The intermediate angle that's seen in chimpanzees tells us that they are, in fact, knuckle walkers. They don't hold it directly upright in the way that humans do. Although it is worth noting that in chimpanzees, it's still more intermediate than it is in like bona fide quadrupedal animals like this raccoon, where it's totally at the back because they're fully quadruped, who hold their heads sort of level or parallel with the ground. Chimpanzees are knuckle walkers who are capable of some, albeit very rare, bipedal locomotion, and so they have, correspondingly, an intermediate foramen magnum, in between a bipedal human and a fully quadrupedal non-knuckle walker, like a raccoon. But Australopithecus, although in the face it does look kind of chimpy, it has a foramen magnum far more like what we see in humans, meaning that it held its body upright, just like humans do in an orthograde posture, and this is not surprising given that's what the entire rest of the skeleton is telling us. Bipedalism would get more efficient in genus Homo, as would running specifically, but Australopiths were very capable when they were on the ground, and as I said, they were on the ground a lot, but they still maintained some characteristics that were related to being efficient in the trees, such as long arms, curved phalanges, and a more dorsally oriented scapula or shoulder blade. Australopiths were the first tool users. They are associated with tools like the Lomequian stone tools and cut-marked bones at Dakika, but their brain cases weren't that much bigger than what we see in chimpanzees, so while there was an increase in Australopiths, it wasn't really anything to write home about. Typically, we associate the explosion in brain case size with the emergence of our genus Homo, which descends from genus Australopithecus. Genus Homo shows up first with Homo habilis and and Homo rudolfensis. It enters into the probably too big Homo erectus, and then we see diversification with out of Africa into the likes of Homo neanderthalensis, denisovans, late surviving Homo erectus out in Asia, Homo floresiensis, Homo naledi back in Africa, and eventually Homo sapiens also back in Africa. Give it a couple 100,000 years, and then Homo sapiens ends up being the only remaining hominin, either by innovation or by chance. Probably both. Cut, print, wrap, and then here we are with one goober ape having a conversation with a bunch of other goober apes using cool technology. This happens over the course of 7 million years, and that's the basic story. Sort of devoid of all of the selective pressures and hypotheses, but that's the basic story of genus Homo and of Homo sapiens. But that's not the whole story, because genus Homo is not the only genus that descends from genus Australopithecus. We have a sister genus that people don't really talk about outside of paleoanthropological circles. Why don't people talk about this sister genus? Because it's a mutant f***ed-up Australopithecus that ate grass, had big-ass teeth, probably sometimes used tools, and whose recreations exceed the standards of the uncanny valley, often looking something like this.
Are you serious?
The name of this genus is Paranthropus. It literally means beside man. And while I love these guys, I absolutely adore them, as I do all hominins, and I find something very charming about how messed up their faces are with those huge flaring zygomatics. Not everybody does, and I think that's for obvious reasons.
Daddy, chill.
What the hell is even that?
Paranthropus kind of messes up the hero's journey of human evolution just a little bit by showing us that genus Homo, our genus, the wise men, was not the destiny of all hominins. Like Homo floresiensis, it shows us that Homo sapiens is not sort of a goal to be attained, but rather probably happenstance amidst many, many selective factors that created many, many successful hominins. Paranthropus is often depicted as like this big cow ape, this critter that sat on the savannah and grinded up grass and vegetation with enormous molars. And truly, the molars are enormous. This is actual size. This is a 3D printed model of a Paranthropus mandible. And I mean, just look at the comparison of the molars to a human mandible. I mean, these things really are impressive, but they don't really match the narrative that we typically see for genus Homo, where you have a plucky hominin like Homo habilis and then eventually Homo erectus, which figures out how to fashion tools and tame the environment around it, becoming Homo the hunter, versus, Paranthropus, the cow ape. What I'm saying is that I think people find the idea that these guys are our sister genus, the closest genus to genus Homo, to be a bit embarrassing, inconvenient, not very dignified. I think that's dumb and ultimately comes from the same sort of human exceptionalist discomfort with the idea that we are apes currently who descended from more basal apes, and that we're just really not that far physically from what came before us. But it also makes me mad because it does not give Paranthropus its due. It doesn't give these guys credit for being a really cool, interesting, successful hominin. Yes, they had huge molars, and yes, they sometimes ate grass, but they also probably used tools. We find Paranthropus teeth associated with butchered hippo carcasses, and while some people are quick to say, oh, actually, that was genus Homo that did that, even though we don't find any members of genus Homo at the site, I think that if we're being consistent, we have to say that at present, it looks like Paranthropus was capable of using tools, and a lot of the same tools that early members of genus Homo were capable of using. They were committed bipeds, evidently very similar to genus Homo in that they would have walked across the savannah upright and in a way that was probably more efficient than what we see in Australopithecus before it. Paranthropus was diverse, just like Australopithecus and genus Homo, with currently 3 or maybe 4 species ascribed to it. The first or oldest being Paranthropus aethiopicus in eastern Africa, followed by Paranthropus boisei, and today's Paranthropus robustus, boisei being also in eastern Africa and robustus being in South Africa, along with maybe a more gracile Paranthropus capensis. And evidently, this diversity mirrors Homo in the details as well. because it is Paranthropus robustus that now represents the smallest known hominin in our fossil record. So that means that we have large-bodied species of genus Paranthropus and genus Homo, and also small-bodied species in members of Paranthropus and genus Homo. So let's talk a little bit about this fossil, STW1/HR2. We're just going to call it Swartkrans 1. Unfortunately, this paper is not open access, so I cannot go through the entire thing, but I'm going to hit you with some highlights, and then we're going to give some thoughts on it. And by we, I mean just me. Well, unless you count the skeleton in the back. It's titled First Articulating Os Coxa, that's a partial pelvis, femur, and tibia of small adult Paranthropus robustus from member 1, the hanging remnant of the Swartkrans Formation in South Africa. In this first figure here, we have a nice map that shows you where we're talking about. In South Africa, there's a region that is generally dubbed the cradle of humankind. The reason that it gets this fun little moniker is because there's just a ton of sites in this one very small location. And I think the reason for this is generally considered to be the karstic nature of the caves. Like, they just preserve really well. These cave systems in the cradle of humankind are just a wonderful spot to find fossils. So in A, you can see here South Africa. There's our location of the cradle of humankind. And then here's a close-up where you can see a ton of very famous sites that a lot of these hominin fossils come from. There's Swartkrans down here in this area that has like Kromdraai and Sterkfontein, a lot of areas that you probably heard of before if you're interested in this. And then we get a nice grid to sort of close up the site itself. Figure 2 is really cool because it shows in situ the areas and like the blocks that these fossils came from. I really love the name The Hanging Remnant Mass. That sounds like a Dark Souls boss, but you can see the highlighted blocks up here from which some of the fossils came as a part of the Hanging Remnant Mass, and C and D show the pre and post excavation pictures. This is super important if you battle pseudoscience like I do, having this kind of resource to show, like, yes, these really were in articulation, and we know because the scientists took pictures. So the introduction that accompanied those first two figures talked a lot about Swartkrans, the site, where they specifically pulled these fossils up, some basically essential background information. Now, Table 1 is important for a completely different reason, because instead of establishing like the location, it tells you the comparative sample to which this new fossil was kind of contrasted to, right? So anytime you find a new fossil, it's not immediately obvious what species it belongs to. What you want to do is run a comparative analysis. You want to take that new fossil and compare it to as many other specimens as possible for which the species is established and known. Table 2 has a comparative neotaphonomic sample of baboon remains, and the reason why this sample exists is because they suspect that this Paranthropus robustus leg, our new fossil, was chewed upon by a leopard. But in order to test that, they have to have, like, modern day examples of bones that have been chewed upon by a leopard to see if the signals match. So they have 4 observed or inferred chewed upon by a leopard baboon remains, and then 1 natural death inferred remains to see whether or not this Paranthropus leg looks like it was or was not chewed upon by a leopard. This is science. Likewise, Table 3 includes all of the measurements that were taken from various landmarks on this leg. So on the preserved portion of the os coxae, from the femur, from the tibia, they have the value of the specific measurements. They have the landmark under measurement, the value under value, and then under reference is the previously established methodology for measuring this specific landmark. So this is, folks, this is how science works. It's like you have to cite everything. So if I want to measure the bicondylar length, I need to look at how the bicondylar length has previously been measured by scientists. And so I'm going to use Boekstra and Ubelacher, 1994, so that when people see that I've measured the bicondylar length and they're wondering how specifically I measured that, they can go to that reference where it is outlined in great detail. The measurements that this team took were extensive. They outline it all in this very long table, and the following table, Table 4, contains the origin, composition, and scanning information for the extant hominoid sample. So they can't just take the leg and compare it to other extinct specimens. You want to have an extensive, extant, or still living hominoid or ape sample to establish some sort of known reference points. So they have a lot of humans involved here, they have a lot of chimps, they have a lot of gorillas, they have a lot of orangutans, and I don't think they have any gibbons, so I'm wondering why they established this as hominoid rather than hominid, but I digress. Figure 3 was taken in a laboratory, and it's essentially the leg, all of the bones still inside the block that was removed. So the bones are in situ within the block that was taken from the hanging remnant. I just think that's a cool little shot of all the bones sort of pre-prep. Figure 4 is that left os coxae, so it's a chunk of one side of the pelvis, and you can see it in several views here. Likewise with the femur, so what you're looking at here again is one bone seen from several different views, so you as the reader can get a good idea what it looks like from superior, inferior, medial, lateral, anterior, and posterior positions. And in figure 6, the same with the tibia, so the shin bone. The femur is the thigh bone, the tibia is the shin bone. And just to let you know, underneath each of these pictures is a multi-paragraph extensive description of what it is you're looking at. All the little lumps and ridges on the bone are described like in excruciating detail. The next section starts to go through the comparison to the other taxa. So comparing this mystery leg, which I've already told you is assigned to Paranthropus robustus, but this ostensible mystery leg is compared to a bunch of other different hominins, and the first way they compare it is by looking specifically at each element, and then the figure that you're looking at now is looking at the femoral torsion, specifically the diaphysial torsion. So what that means is, how does the femur twist, right? How does the top of the femur and then along the shaft, how does it actually twist or contort? Which is a feature of a lot of different hominins, including humans, but to different degrees. So they wanted to find out which hominin did the torsion that we see in this femur look most like. Now, technically, that torsion is being used as a proxy for femoral neck anteversion because torsion in the shaft is correlated with torsion in the neck, but all you need to know is that what we're basically looking at here is what does this fossil look like in the upper portion of the femur, of the thigh bone, and in the pelvis? Which hominin does it look most like for which we can compare? And the ones that they compared it to are the hominins for which we actually have like pelvic material for, which is Australopithecus sediba, which we have some really wonderful pelvis material from. Other Australopiths is going to be any other Australopith for which we have that pelvic material to compare to, and in C they list AL2881, that's Lucy, along with several other South African and Eastern African Australopiths. They compare it to early genus Homo. Again, they're doing the comparison to ones for which we have the material for, so Eastern and South African hominins, as well as some hominins outside of Africa. And then they compare the same material to like modern Homo, so that's humans, right? And they compare it for several different features that you really don't need to know the details for. All I want you to take away from this table, unless you really want to dig into it yourself, is that Australopithecus sediba is the closest in morphology to this mystery hominin. Before we move on to other comparisons, I do want to harp on one point here, because this is missed by a lot of people, I think, when talking about Paranthropus and the nature of Paranthropus, because we just don't have that much postcranial material for it. And that's this little sentence here. The os coxae of Swartkrans 1 indicates less ambiguously than does its proximal femur that the individual engaged in terrestrial bipedalism. Despite the fact that it's very fragmentary, it's incredibly robust, even compared to the pelvis of other Australopiths, or the pelvies of other Australopiths. So yes, Paranthropus was bipedal. We knew this already from the position and angle of its foramen magnum, as well as from the postcrania that we have, but this really helps cinch it even further. Now, there's really not much in the way of definitive Paranthropus pelvies for comparison, so it's really not surprising that the thing that it grouped most closely with was Australopithecus sediba, but we do have several femoral necks from Paranthropus, like from other species of Paranthropus to compare it to. So if this thing belongs to a member of Paranthropus, it should probably group with other members of Paranthropus for this feature. And indeed, they have the presumed taxon, the specimen, the angle of the femoral neck, the Merrick index, and the source for that measurement or for that publication of that measurement. And here we have Australopithecus afarensis, that's Lucy's species, Australopithecus africanus, Australopithecus sediba, Australopithecus prometheus, if you believe in that kind of thing, and then two members of Paranthropus, and indeed, Swartkrans 1 is grouping with Paranthropus robustus. And likewise, to simplify, when CT scanned at the cross-section, we get another signal that lumps Swartkrans 1 specifically with Paranthropus robustus to the exclusion of Homo sapiens, Paranthropus boisei, and Australopithecus afarensis. I will note too that cross-sectioning the femoral neck itself shows a biped signal, just for the creationists out there that want to argue that Paranthropus is like a knuckle walker or something. And actually, while I'm on this point of this leg indicating that Paranthropus robustus was a biped, I'm going to zip down to a really important line that I'm going to pocket for later discussions with creationists generally, whenever they argue that Australopithecus or Paranthropus, usually they lump in with Australopithecus, weren't bipedal, because in talking about the history of people wondering about the nature, like the precise nature of Paranthropus locomotion in general, they go on to talk about how this particular fossil contributes to the question of like, how did Paranthropus move? They say it is in this context that Swartkrans 1 fossil set, the Swartkrans 1 fossil set, with its more secure taxonomic attribution, so they're saying this thing is pretty reliably assignable to Paranthropus robustus, and so since this thing is Paranthropus robustus, it can tell us a lot about how Paranthropus, the genus, moved, is a singular and particularly valuable source of information about the locomotor adaptations of Paranthropus robustus. And in summary, the external morphology of all joints and limb bone diaphyses of Swartkrans 1 set show morphology well suited for stabilization during orthograde and bipedal loading and for resistance to torsional and shearing forces that are commonly experienced by primate habitual bipeds. These observations alone lead to a fundamental conclusion. The species Paranthropus robustus, as exemplified by this fossil set, was a competent, probably habitual terrestrial biped, and then this is the take-home, regardless of the precise details of its gait kinematics. Moreover, the modern human-like tibial arch angle of this fossil hints that at least some Paranthropus robustus individuals may have possessed a developed longitudinal arch. I need you guys to understand the importance of this little bit right here. When Lucy was first uncovered and published by Johansen and colleagues, there was this massive debate about the details of how her species, Australopithecus afarensis, moved. There were some, like Lovejoy and colleagues, who argued that she effectively moved upright just like a human did, and there were others, like Stern and Sussman, who argued that Lucy, while she did move upright and bipedally when on the ground, had a gait that was a little bit different than modern humans, a little bit more primitive, and that she still spent time in the trees. And this led to a big rigmarole about the details of Australopith locomotion that was co-opted and used inappropriately by, oftentimes, creationists who wanted to propose that there was a debate as to whether or not Australopithecus was a biped. The debate was never about her bipedalism, it was about the nature, the details of that bipedalism and how much time she still spent in the trees. These guys are making it abundantly clear that this pelvis, this leg, looks like that of a biped when this critter was on the ground, regardless of the minutia of how that bipedalism looked. They go on to say, if Swartkrans 1 climbed routinely, there is scant indication in the surface morphology of its lower limb bones that it did so in the ways and or frequencies observed in extant non-human apes. So what they're saying is that it's like, yeah, this thing may have climbed, but there's nothing in looking at these limb bones that suggests that it looked like an orangutan in the trees. This thing is its own animal, and in addition to the bipedalism that it certainly practiced, it may have also climbed, but we can't tell that by just looking at the leg. But these guys know how paleoanthropology and how paleontology generally works, and so they go on to say, Wait a second, we're not saying it didn't climb. They say, moreover, none of these observations, regardless of their associated taxonomic certainty or uncertainty, can be used to suggest that Paranthropus robustus never climbed. For example, important behavioral and morphologic studies of modern human foragers show them to be quite capable climbers, but without betraying that advanced capacity in their external bony ankle morphology. So they're basically saying, like, when we look at the leg, it doesn't look like the leg of modern apes that spend a lot of time in the trees. It looks like that of something that moved bipedally on the ground a lot. But that doesn't mean it never climbed, because modern humans also have legs that look like that of something that spends a lot of time bipedally on the ground, and modern humans climb all the time. They say these foragers climb regularly to collect valuable foods, such as honey. Given their small size and arboreal ancestry, there is good reason to assume that early hominins, including Paranthropus robustus, were also motivated to climb at least occasionally to meet various fitness-enhancing goals, such as food, shelter, and avoiding predators. This is straight up because of all the misunderstandings regarding Lucy's discovery and thus Australopithecus afarensis' locomotor style. They're basically saying, like, look, the signal that we're getting is that of a biped. Does that mean it never climbed? Absolutely not. In fact, modern bipeds do climb with evident bipedal morphology in their legs. But all of this is really important in part because of the details of this fossil specifically. The fact that this fossil is one of an upright biped when on the ground that doesn't have any obvious arboreal signals is contrasted with the teeny tiny size of this thing and the fact that it was chewed upon by a leopard. Figure 19 shows us just how tiny we're talking about here. So here we have our extant specimens on the far left, and on top is femurs all across the board, highlighted by my cursor, and below is tibias, highlighted by my cursor. So here's your thigh bone, and here is your shin bone. Pan is chimpanzees, and the Khoisan and MH stand for living human populations. So as you can see, humans have really long legs. Here's the human femur, modern human femurs, again highlighted by my cursor, compared to a modern chimp femur. Same with the tibias, and what we're basically seeing is humans have really long legs. The closest thing to a human in our fossil taxa is KNMWT 15,000, or Homo erectus / Homo ergaster, which has similarly a very long leg. Some of our shortest specimens are depicted by LB1, that's Homo floresiensis, the 3.5-foot tall hominin, and even shorter than that is Swartkrans 1, our little Paranthropus robustus here, who has an even shorter femur than LB1 and an even shorter tibia than LB1. This hominin was teeny tiny, but it was also bipedal, and the morphology of the femur, tibia, and pelvis matched that most closely of Paranthropus robustus, meaning this thing didn't have a big brain. It was basically a pinhead, not unlike other members of Paranthropus. Small brain and teeny tiny body size makes you easy prey for a leopard, which evidently this individual was, because its pelvis looks like a leopard chew toy. It has all these like gnaw marks on the edges of it, which again the paper specifically looked at. All of this together paints a pretty clear picture with a pretty clear lesson. The picture is that of early members of Paranthropus, and probably early members of genus Homo, being small-bodied and small-brained. Obviously, there are extremes on either side there, and capable of using some tools. Their morphology is clearly that of something that was a very competent biped when on the ground. However, because of their small brain size and small body size and limited tool use, they would have made easy prey for predators like leopards, and evidently they did make easy prey for predators like leopards, because we find leopard tooth marks all over their bones. So what is a small-brained, small-bodied, limited tool-using hominin to do? Climb into the trees for safety and shelter and probably food as well. The fact that this fossil reveals a very small body size for some hominins provides yet another reason for these hominins to maintain some ability in the trees, the signal of which we usually see in their arms and shoulders. But the fact that this is a leg with clear bipedal adaptations and no arboreal signals means that these hominins, even when very small-bodied, were experiencing a massive pressure to be efficient on the ground. What kind of environment would we expect these guys to have been living in for such a powerful pressure for efficient bipedalism combined with maintaining arboreal adaptations? Well, Let's take a look. This paper on swartkrans, titled New Modern and Pleistocene Fossil Micromammal Assemblages from Swartkrans, South Africa, Paleobiodiversity, Taphonomic and Environmental Context, tells us that swartkrans had an environment that was an open landscape primarily covered by grassland vegetation, so flat without trees, but they also featured components of wooded areas, rocky outcrops, and the proximity of a river. If you are an ape forced to adapt some form of bipedalism because of an environmental change that's getting rid of trees and forest cover in favor of grasslands, you're going to get adaptations for bipedalism because you don't have the trees to hang around in anymore. But if there are still clumps of trees, you can go up into those trees to avoid predators, to find food, and to make shelter. You are going to experience a massive amount of selection to maintain some ability in the trees, an ability that modern humans also maintain to a lesser degree, despite the fact that very little of our anatomy reflects arboreality. In ecology, there's this concept called fallback foods, where the morphology of the teeth are basically best adapted for processing a specific type of food, but that food type isn't the preference of the animal. So in the case of gorillas, their teeth are really well adapted for shredding leaves, but they don't like leaves very much. They'll only eat leaves when there isn't enough fruit to go around. So even though their primary diet consists of a whole lot of fruit, their anatomy reflects that of a folivore because they need to be able to process those leaves often when fruit is scarce. So gorilla anatomy suggests they are folivorous, but gorilla behavior reveals that leaves aren't the only thing that they eat. We're seeing something similar, I think, with Paranthropus robustus here. The leg is clearly that of a biped. There is no doubt that it moved bipedally competently, but that doesn't mean it didn't climb. In fact, its tiny diminutive body size, the smallest of any hominin found so far, and evident predation by leopards kind of necessitates it. So I know what you're thinking. You're thinking, oh shoot, oh no, if only we had some kind of Paranthropus arm, because then we could know with certainty if they maintained some adaptations for arboreal behavior. Great news! In this 2020 paper titled The Upper Limb of Paranthropus boisei from Illoret, Kenya, they describe an arm from Paranthropus boisei. Now granted, it's not Paranthropus robustus, but it is the same genus. So what is the signal from this animal? The conclusion is pretty clear. Like its Australopith predecessors, Paranthropus boisei most likely climbed trees as a part of its typical activity regime. A more laterally oriented glenohumeral joint implies that arboreal locomotion may have been a smaller part of the positional repertoire of Paranthropus boisei than has been suggested for taxa like Australopithecus afarensis, but apart from this, K&M ER 47000 exhibits a suite of features that are consistent with arboreal climbing. And I would even argue that you could say that to a lesser degree about humans as well. Our pectoral girdle still maintains signals that allow for arboreality, even if it's not as efficient as the type of arboreality that you see in other extant apes. Our shoulders are still extremely mobile, and compared to most non-ape primates, our arms are very long for our body size. It's just that our legs are like super long. As the paper said, modern human foraging societies still climb all the time. And I don't know about you, but whenever I watch Olympic climbers, I'm pretty impressed by the speed and agility. It's not like we're helpless in the trees. So we have a little bit of a twofold moral here, don't we? The first one is more complete skeletons are always better. If we only had the leg of Paranthropus, we would probably assume that it was exclusively a biped. And if we only had the arm of Paranthropus, we would probably assume that it spent a whole lot of time in the trees, but having them both together reveals a much more nuanced picture. Of course, there's more to it than that, but I'm simplifying here. Moral 2 is that the total morphology of an animal can absolutely tell you what a critter was capable of doing with regard to its locomotion and its diet, but it doesn't necessarily confirm that that's all it was doing. And we can actually investigate the full suite of possibilities by moving outside of the morphology of a single individual. We can include other individuals. We can include closely related taxa. We can include stable isotopes. We can include taphonomic signals. All in all, Swartkran's one of the hanging remnant is a fascinating fossil because it confirms for us the bipedal capabilities of Paranthropus as a genus, and it reveals that Paranthropus, like genus Homo, was extremely diverse in its body size and locomotor capabilities. There's a lot more we could get into with regard to this paper. We could talk about why they haven't identified it as a female, even though it's really small, and we know that Paranthropus is super dimorphic. It turns out that signals in the pelvis for sexing males versus females is even less reliable in more ancient hominins than it is in modern humans. We could talk about the taphonomic analyses that they ran and how they figured out that this thing was in fact gnawed upon by a leopard. And we could talk a little bit more about the taphonomy and how cool the articulation of this leg was, but this video is already really long, so I'm just going to end it here. My gentle and of course very modern apes, thank you so much for being such a curious primate being here. If you want to support my channel in a free way, you can do that by liking, commenting, and subscribing. I don't think it is of any great hassle to you to do so, but it really helps me with regard to the algorithm. And if you want to support me in a more financial way, you can do that by joining my Patreon. Patrons get access to videos early sometimes these days, but they do every time virtually get their names at the end of the video, which is going to happen here in about 2 seconds. Thanks for being here.